Okay, so the topic of today's lecture is UML class diagrams and the relationship between classes. All right, so there's this thing called UML that's used to describe the structure and behavior of object-oriented software. So UML stands for Unified Modeling Language. It's a visual language used in software engineering. And it's used to visualize the architecture or the design of software. So it's a visual language, which basically means you draw pictures. It's a language where you draw pictures. Right? And you can draw a picture of the UML language. Right? So I can draw a UML diagram of the UML language. And so the way the language is organized is you've got this thing called a diagram. Right? So all UML I guess all UML descriptions are basically diagrams of some kind. Right? What kinds of diagrams can you have? Well, you can have diagrams that illustrate the behavior of a program, or you can have diagrams that illustrate the structure of a program. We're interested in the structure. We're not so much interested in the behavior diagrams in this course. Right, so in your structure diagrams, you've got things like class diagrams or component diagrams, object diagrams, and all sorts of other diagrams. And for our purposes, we're really interested in these class diagrams. So we want to know how are classes related to one another in a program. So the UML class diagram describes the structure of a class, right? So of a single class. Well, not necessarily a single class. It describes the structure of a class or classes. The simplest diagram that you can have is just a box, right? So the simplest class diagram includes the name of the class. Right? But you can show other information about the structure of a class as well. Right? So I can show what fields make up an object. I can show what methods belong to a class. So that's the simplest UML class diagram that you can draw. Right? It's just a box. So the box indicates the class, and then the name of the class. Right? So that's the simplest version of the UML class diagram for our point 2 class. Right. There are some standards on how you generate these diagrams. Whether or not you actually have to adhere exactly to those standards, not so important in this course. Right? It's important that you see these class diagrams, especially if you take one of the other software design courses in 3rd and 4th year. Because in those classes, they will use these diagrams a lot to describe the structure and the behavior of a program. If you want to, you can illustrate the fields of an object. Right? So for the point 2 class, right, we have 2 fields, x and y. Right? Now, UML is language neutral, so it's supposed to be able to describe any object-oriented program written in any object-oriented programming language. So the names that UML uses are often different than what Java uses. Right? So for example, the fields are UML will call attributes. And the methods UML will call operations. So you can show the attributes x and y. Right? You can see here that they both have type double. Right? So again, it's language neutral, so it doesn't use the same syntax as Java. Right? The minus sign here indicates that the fields are private. Right? And you can include other, the UML has support for the other access modifiers as well. Right? So we have public and private. Later, we'll talk about package private and protected, right? But you do have symbols to represent those types of access modifiers as well. If you want to, you can then show the methods of your class, right? Or you can just show the methods of the class. Right? You don't have to show the fields. You don't have to show the methods. You can show the fields, or you can show the methods. Right? So the methods of the class then are shown. If you want to show them, you show them in another box. Right? Your methods can have access modifiers. Right? They have a name, then the parameter list, and then the return type. Right? So the order of the elements is different in a UML class diagram compared to the Java programming language. Right? So for example, our point 2 class has a public constructor called point 2, right, that has no parameters, returns no value. So the return value comes at the end in a UML class diagram. Right? We've got 2 other constructors here that are both public. We have a method called x, right? That returns the x coordinate of the point, right? So that returns a double value there. Right? You've got a method called y that returns the y coordinate of the point, so that returns a double there, right? And so on and so on and so forth. Right? So this gives you a very compact representation of your class. Right? Ranged value is a type of it's a class that represents a value that lies between some minimum and some maximum value. Right? So it's a value that's represented as a double. Right? It lies between some minimum and maximum value. So that thing there is represented as a range, right? As a range object. Right? Our range value class has a constructor that takes in the minimum and maximum value of the range, right? And the value that should lie between the minimum and maximum value. Right? You can ask for the minimum and maximum value. You can ask for the range object that represents the range, and the value, and so on and so on and so forth. Right? So this was an assignment from, I think, last term to implement this class. Okay, our point2 class implements the comparable interface. So if you want to show that on your UML class diagram, you use what's called the Lollipop notation. Right? So you draw your point2 class. Right? If you want to, you can put in the fields and methods here. Right? Then you draw a solid line and a circle, and beside the circle you write the name of the interface. Right? So this just says point2 implements the comparable interface. Right? That says ranged value implements the comparable interface. Right? And you can ask if you had a list, if you have an array list, right? So if you wanted to draw the array list UML class diagram, you would just draw a box. Right? You would say array list. And then if you wanted to, you can indicate that it implements the list interface. Right? It also implements the collection interface. So you could write that as well if you wanted to. And so on and so forth. Right? So again, the UML class diagrams are meant to be compact representations of your classes. Right? And so we're going to use these UML diagrams, UML class diagrams, to describe how classes are related to one another. Right? Now, so far, all of the classes we've made, all their fields have been primitive values. Right? So we haven't actually had to talk about relationships between classes. But as soon as you start to design classes where the fields are actually reference types, right? So in other words, your classes, your objects are made up of other objects, then it becomes important to be explicit in how those internal objects are related to the object that they're in. Right? So in an object-oriented program, typically it's made up of many interacting classes. Right? So you have objects of those classes, and those objects interact with one another. Right? The relationship between those classes is important in an object-oriented programming language. Right? So your program is built by, is made up of many objects. Right? So in other words, there's lots of classes in your program. So that describes the structure of your program. Right? A large object-oriented program might have literally thousands or tens of thousands of classes. Right? Classes interact with other classes, right? So objects can call methods belonging to other objects. That describes the behavior of the program. Right? And that's described by a whole other set of UML behavior diagrams. Right? So we don't even talk about these in this course. We're only interested in the structure diagrams. Right? So what's the weakest relationship that you can have between two classes? Right? So the weakest relationship you can have between two classes is one called dependency. Right? So dependency models the uses relationship, right? So if a class uses another class, then that class has a dependency on the other class, right? So if class X uses a class Y, we say that X depends on Y, right? Now, Y might also use X, right? So dependency can be a two-way relationship, right? Just like in real life between people, right? How can you tell if X depends on Y? Well, you just look at your class X. Right? If there's a mention of Y anywhere in the class, then X uses Y. Right? So if X has a field of type Y, then X uses Y. Right? There's a dependency relationship. If X has a method that has a parameter of type Y, then X uses Y. Right? If inside a method or a constructor you use the class Y, then X depends on Y. Right? If inside a method you return an object of type Y, then X uses Y. Right? So in other words, if your class has any mention of the type Y, then it uses Y. Right? So if we look at the point2 class, for example, right? So there's the point2 class. You see that one of its methods, right, takes in a vector2 object. Right? So we say that point2 depends on vector2. Right? You also see that there's a word, object, divide, negate. Where's, I'm looking for equals. Here we are. Right? So the equals method takes in a reference to a big O object. So point2 depends on object. Right? And then somewhere there's a toString method. There it is. Right? So there's a method that returns a string. So our point2 class depends on the string class. Right? Now, if you want to show the dependency relationship on a UML class diagram, then you draw your classes. Right? So here's point2, vector2, and string. Right? And then to show the dependency between point2 and string, right, you draw a dashed line and an open arrow pointing at string. Right? So this says that point2 depends on the string class. Right? It says that vector2 depends on the string class, right, because vector2 also has a toString method. Right? And it says point2 depends on the vector2 class. Right? If you look at the vector2 class, I don't think there's any method that uses a point2 object. So it's not the case that vector2 depends on point2. Right? When you look at this diagram, what does it tell you? It says if I make a change to vector2, right, then that potentially affects the point2 class. Right? So if I make some changes to the methods in vector2, that potentially affects the way that point2 works. Right? If I make a change to string, that potentially affects the way that point2 and vector2 work. Right? You might have to recompile, you might have to edit your code, you might have to do something. Right? You might not have to either, right? But that's what dependency means, right? Any changes to that class affects any class that depends on that class. All right, so dependency, that's the weakest form of, that's the weakest relationship between two classes. Association is a stronger form of dependency, okay? So association, so dependency models the uses relationship. Right? Association models the has-a relationship. Right? So if a class X has a field of type Y, then we say that X has an association with Y. Right? So it's no longer the case where you just have a method or a constructor that uses Y. Here you have to have a field of type Y. Right? Now it can also be the case that Y has an association relationship with X, which is a little strange, but it can happen. So association is also allowed to be a two-way relationship. Right? So in other words, X might have a field of type Y, and Y might have a field of type X. So to show an association relationship using a UML diagram, you use a solid line connecting the two classes. Right? So this says that the ranged value class has an association relationship with the range class. Right? The one here is called a multiplicity element. Right? So the one on range says that range value, right, has an association with one range object. Right? In other words, every ranged value has exactly one field of type range. Right? Whether or not that multiplicity element is here is optional. Right? So you don't have to, the information that you choose to show on a UML class diagram is context dependent. Right? So depending on what you're using the diagram for, you may not need to show that multiplicity element there. Right? Notice that this says in assignment 3, that was assignment 3 from last term, I think. It was either last term or last year. Right? There was this ranged value class that had to be implemented. Okay. There's actually a note down here. So it actually says the relationship between range value and range is actually stronger than just plain old association. Right? We'll get to that in a minute. Okay, here's an example of a fairly complicated UML class diagram. So there's a class called show, so that represents a live performance of some kind, right? Broadway show or something like that. And then there's a class called performer, which represents a performer in the show. Right? Now that line there, right, indicates that there's an association relationship between show and performer. Right? You're allowed to label that relationship. So that relationship there, that's the orchestra relationship, right? So you can have performers that are members of the orchestra for that show. Right? Now, what do the stars mean? Right? So you have show, line, star, performer. Right? So that says that a show can have 0 or more, or any number of performers in its orchestra. Right? Going back the other way, this says that a performer can be a member of the orchestra in any number of shows. Right? Which is not uncommon if you're someone who plays an instrument for a living, right? You might be a performer in many different shows. Now, what about the cast? Right? So for the cast relationship, a show can have any number of performers in its cast, right? And a performer can be a cast member of any number of shows. Right? And finally, association, you can have an association between two objects of the same type. Right? So in the backup role, so if you're talking about, right, so we're trying to describe the role of a backup to a particular role. Right? So you can be, the understudy can back up, right, 0 or 1 lead performers. Right? A lead performer might have any number of understudies who are backing them up. Right? So association can be a two-way relationship, and it can even be a relationship between objects of the same type. So if you're implementing that performer class and you're doing the backup role, right, the performer class would actually have a field of type performer, right, indicating the backup role. Okay, aggregation and composition. Oh, any questions so far? Great. Aggregation and composition. So these are both stronger forms of association, which means they are also stronger forms of dependency. So the terms aggregation and composition are used to describe the relationship between objects where there is a has-a relationship between the objects, right? So just like association. Right? So in other words, in aggregation and composition, right, the aggregate or the composite object, right, has a field of some other type, right? Has a field of some other reference type. So for example, right, the university might have a collection of departments. Right? Each department might have some sort of collection of professors. Right? Now, composition, right, so there's two different relationships here. Composition is the relationship that implies ownership. Right? So what does that mean? So if Queens was to disappear tomorrow for some reason, right, all of its departments would also disappear. Right? So what that means in a programming language is if a university object goes away, right, so it gets deleted for some reason, right, then all of the objects that it's made of also go away. Right? So all of its department objects, they also get deleted. And so in other words, the lifetime of the parts, right, the departments, depends entirely on the lifetime of the owner, right, the university. Right? So usually we call in this case the university, we would say that's the whole, right? The departments would be called the parts. Right? So a university is a composition of departments, right? Because the university actually owns its departments. Aggregation does not imply ownership. So aggregation is the weaker form of, so it's stronger than plain old association, but it's not as strong as composition. Right? So in aggregation, right, if a department were to disappear, so for example, if the School of Computing was to disappear tomorrow, right, its professors don't disappear. Right? So in other words, its professors will get scattered out to the rest of the university somehow. Right? So in other words, the department does not own its professors. Right? The professors can live, the professors exist, right, can exist in isolation of the department. So we say that a department is an aggregation of professors. Right? The department has a bunch of professors, but it doesn't own them. Right? The university has a bunch of departments, and the university owns the departments. Right? So composition is the stronger form of this relationship. Right? These are both types of ownership. It's just that aggregation is shared ownership, right? Whereas composition is exclusive ownership. Right? Now, both aggregation and composition are one-way relationships. Right? So a department is an aggregation of professors, right? But a professor is not an aggregation of departments. Right? In other words, I am not made up of a bunch of different departments, right? But a department is made up of a bunch of different professors. Right? Similarly, a university owns its departments, right? The departments do not own the university, right? It's strictly one-way relationship in both cases, right? Whereas an association, it can be a two-way relationship, right? So that's why aggregation is a stronger form of association, right? Composition is stronger than association. Composition is stronger than aggregation because composition also implies exclusive ownership, right? All right, so aggregation is by far the simplest aggregation is the simplest relationship to implement in a class, right? So why is it the simplest? Well, you'll see why in a second, right? Okay, so I want to make this person class, right? This is a very common type of class that's used in introductory programming courses. It's kind of useless as a class, honestly. Like, it doesn't have any real purpose other than to illustrate a point. Right? So a person might have a name and a date of birth. Right? Now, how am I going to represent the name and date of birth? Right? Well, I can represent the name using a string, and I can represent the date of birth using this class called date. Right? So date is Java util.date. Right? So it's a class that represents basically a time in Java. Okay? They're both reference types. Right? So I now have some sort of relationship between the person class and the string and date classes. Right? There's a string and a date field, so I know that the relationship has to be association. Right? And in fact, in this case, it's going to be aggregation. Right? So in other words, a person object is made up of a string and a date object. Okay? So in the constructor, I'm going to implement the constructor this way. Right? So someone's going to pass in the name and birth date of the person, and I'm just going to write this dot name equals name, and this birth date equals birth date. Right? Now notice what's not happening here. Right? I'm not making a new string object to represent the name. Right? I'm not making a new date object to represent the birth date. Right? I'm saying this name is the same object as that name. Right? And I'm saying this birth date is the same object as that birth date. Right? So there's no new object being created in the constructor here. When someone asks for the name of the person, we simply return this dot name, right? And when someone asks for the birth date of the object, we simply return this dot birth date, right? So this is exactly what you would have written for any of the classes you've implemented so far that return primitive values, right? So when you return the x coordinate of a point, you just return this dot x. If you were to return the y coordinate of a point, you just return this dot y, right? So exactly the same as everything we've done so far. Right. Now, this example uses aggregation, right? So the constructor does not make a new copy of the name and birth date objects passed to it, right? What does that mean? So that means whoever called the constructor, right, has a reference to the string object that represents the name. They have a reference to the date object that represents the birth date, right? Now, the person object also has a reference to its name and birth date object, right? But now there's two different people, right, that have references to the name and birth date. Right? So both the client or the caller of the constructor and the person object, right, they have references to the same name and birth date. So if you create a person object in the following way, right, so S is the string, Billy Bob, D is the date, March 26, 1991. Don't worry about actually learning how to use the date class. It's an old class and you're discouraged from using it. Right? It's useful in this example, though. It's hard to use, too. Like 91-226, you have to figure out that means March 26, 1991. And then you make the person object passing in S and D. Right? So if you were to draw a memory diagram of this picture, of this program, what you would get is the following. Right? So S is the string, right? D is the date, P is the person. Right? So what is S? S is the string object that lives at address 250. Right? So if we go to address 250, there's our string object. Right? D is the date object that lives at address 350. So we go to address 350, and there's our date object. P is the person object at address 450. So there's our person object. Right? Now, when you look at the fields of the person object, right, there's a field called name, there's a field called birth date. Right? what does the name field point to? It points to the object at address 250, right? So in other words, it points to the same string object that the caller of the constructor has, right? The birth date points to the address, object at address 350, right? So in other words, it points, right? They both point to the same date object, right? So the person object has references to a string object and a date object, and the caller of the constructor has references to the two same objects, right? In other words, no one has exclusive ownership over that or that. Right? So what happens if the caller of the constructor changes the date, right? So they set the year to 1995, they set the month to November, and they set the day to 3, right? So in other words, they take their date object and they change it to November 3rd, 1995, right? If you ask the person object, what is your birth date, right? It's no longer March 26, 1990, right? It now becomes November 3rd, 1995, right? Which is strange because the person object has a date, has a birth date, has a name, right? Has a string that's a name, right? Without using the person object, you can change the date of the person object, right? So nowhere in here did I write p dot set birth date to something else, right? Or p set birth, or something like that, right? I never asked the person object to change its birth date, and yet it still changes, right? And that's because whoever made the person object has a reference to the date, to the actual date object that represents the birth date, right? So the date instance is shared, right? That object is shared by the caller of the constructor and by the person object, which means the caller of the constructor can modify the date, and the person object sees the modified date, right? In other words, the birth date of the person changes. Similarly, if inside the person class somewhere the person object changes the birth date, then the caller's date object also changes, right? So the person can change the date, and the caller who made the person can also change the date, right? No one actually owns that birth date object, the date object, right? Now there's something different about the name, right? So the string instance, it's shared by the client, by the caller, the caller of the constructor, and the person object, right? But strings are immutable, right? You cannot change a string once it's been created, right? So back here, right? So if here, right, the caller writes s equals something else, I need a made-up name. We're going to use Bart Simpson. Right? So if the caller writes that on, like right here, right? So if the caller sets s to be the string Bart Simpson, the person's name doesn't change, right? What does that do? Right? That makes a new string called that makes a new string object Bart Simpson, right? And says that s now points to that new string object, right? But that doesn't change the string object pointed to by birth date, right? So that string instance is shared by the client and the person instance P, but neither the client nor P can modify the actual string object, right? Which means even if the caller writes something like that, the person's name doesn't change, right? The only way to change the name of the person is to go into the person class and write something like p.name equals, or sorry, this.name equals something else, right? So in other words, to change the person's name, you actually have to ask the person object to do it, right? And so what's the implication of that, right? The reason this is true is because string is immutable, right? No way to change a string once you've made one, right? So immutable objects make great building blocks for other objects, right? Because I've used a string, I'm no longer worried about the person's name suddenly changing if someone else changes their string reference, right? You can freely share an immutable object and never worry that its state will change, right? And that's kind of a big deal, right? Okay, so how do I draw the UML class diagram for this particular class? Right? So we have the person object, right? The person object is made up of a date, one date, right? It's made up of one string, right? But the relationship here is now aggregation. So to show an aggregation relationship, you use an open diamond, right, on the whole object, right? So we say that person is made up of a date and a string. It's the whole object, the date and the string. Those are the part objects, right? So on the whole object, you draw an open diamond and then a solid line connecting it to the part, right? So person is an aggregation of one date. Person is an aggregation of one string. Here's another example of aggregation. So this is the bouncing ball program. Right? I think I showed you this once before. Now that bouncing ball, that's just a point mass that's falling under the influence of gravity. Right? And you guys all took physics in first year, so you know exactly how this thing behaves as a function of time. Right? The position of the ball is just the velocity times the. So if it moves by some, if it moves in some time dt, right? It moves. Its position changes by the velocity times dt, right? Plus 1/2 g times dt squared, right? So you learned these equations in first year physics, right? The velocity of the ball changes by g times dt, right? In other words, it changes by the acceleration times the time period. Right? So you should all be familiar with these equations, right? You might have seen them broken out into scalar form, but it's all the same thing, right? So in that little program, which I'll show you in a second, right? The way I've implemented that bouncing ball is with a class called projectile, right? That projectile has a 0.2 object that represents its position, right? P. And it has a vector 2 object that represents its velocity, right? So V. And it's got one of those, right? So it's got one point that represents its position. It's got one vector that represents its velocity, right? And I've used an aggregation relationship here. So in other words, inside the projectile class, right, you can guess, right, that there is a point object that represents the position. There is a vector object that represents its velocity, right? So every projectile has a 0.2 object. Every projectile has a vector 2 object. Right? Oh, it's right here. Haha, sorry. So there it is. Right? How do you implement the constructor? So the no argument constructor, right? I have to, what does every constructor do? It has to set that and that. Right? So the no argument constructor sets the projectile at starting position 0, 0, and it has a velocity 0, 0. Right? So in other words, it's just sitting still at the origin. Right? So the position is a new point, and its velocity is a new vector. Okay, now if I ask for the position of the projectile, I simply return this position. Right? So this is exactly what you would have done if I was to ask you to implement this class today. Right? To get the velocity of the ball, you simply return the vector corresponding to the velocity. Did I write? Oh no, I've changed the name. Sorry. This.pos, this.vel. Okay, I can change, or I can let somebody change the position of the projectile. Right? In this case, it returns the old position of the projectile. Right? So if I want to return the previous position of the projectile, right, I have to remember what the old position is. So that's just equal to the current position. And then I set the current position to whatever the caller has asked me to. Right? And then I return the old position. Right? Notice what hasn't happened here, right? I haven't made a new point object here, right? I just say this position equals P, right? So that point object and that point object, they're the same point object, right? Similarly with the velocity, right? I'm going to return the old velocity, so I remember what the current velocity is. Then I set this.vel to V, and then I return the old velocity, right? Again, what's not happening here? Right? What isn't happening here is that I'm not making a new vector here. Right? Whoever called this method, right, their vector is the same as this.velocity, this.vel. Right? It's the exact same object. And here's move. Right? So move just implements those two equations there. Right? So for move, you take the position, right? You add the velocity times dt, right? And then you add 1/2 g times dt squared. Right? For the velocity, you just add g times dt. Right? And that's how you do it using the position and vector, point 2 and vector 2 classes. Right? Notice here that because Java doesn't let you override doesn't let you replace the arithmetic operators, writing arithmetic stuff in Java, writing mathematical stuff in Java is a little awkward. Right? If I want to add something, it'd be nice if I could write p plus something. Right? Unfortunately, I have to use a method called add. Right? If I want to multiply two things, it would be nice if I could write it as something times something. I have to use a method called multiply. Right? Okay, so I mean that's not hard to do, right? What I just showed you, pretty easy to do, right? There's nothing terribly complicated there. You might struggle a little bit writing those 2 lines of code, right? But if you poke around in the documentation for the classes, it's not hard to figure out, right? So it's easy to do, right? Your fields. Well, I got a velocity and I got a position and a velocity, right, as a point and a vector. But those are just references to objects that the caller is always giving me, right? Our accessor methods, right, the ones that return the position and velocity of the projectile, right? I don't do anything. I just return the fields, right? So I just return this dot position and this dot velocity, and away you go. The mutator methods, right, so the ones that change the position and velocity of the projectile, right? We don't do anything. We just set this position equal to p and this velocity equal to v, and that's it. You're done, right? Okay, so what does that mean? It means that the objects inside the point 2 and vector 2 objects inside every projectile object, right? They're just, right? That thing just refers to some object that somebody else is going to give me, right? And that velocity thing, that's just going to refer to some object that someone else is going to give me, right? So in other words, right, the fields are just references to existing objects, right, that somebody else might also know, right? So someone else might also have references to those objects. So our fields are what are called aliases, right? They're just names, right? It's just a different name for an existing object. There's no new object owned by the projectile. Right? If you want to look at the whole source code for this, right, you have access to it, right? It's in this class here, right? So it's in the same class, in the same package that the point 2 class is in, right? You want to look for the projectile class, right? And if you want to run the program, it's the bouncing ball program. Right? So what's going on here? So if you were to draw the memory diagram of making a ball, making a bouncing ball, right? So the caller has a vector called POS, right? That's the position. Sorry, they have a point object called POS. They have a vector called VEL, right? So their point object is at address 250, so there it is, right? So there apparently we've got the position of the ball is, their position is 1020, right? Their vector is 1, 2, right? And we've made a projectile object, and that's right here. There's another constructor that I didn't show you, sorry. There's a constructor, oh, it's not here either. There's a constructor that looks like this, public, or there's supposed to be one anyway. Projectile, point 2, and vector 2. Right, to implement that, you're just going to write this position equals that position, and, sorry. Vector 2, and this dot velocity equals that. Okay, so that constructor is supposed to be there. Right, again, we're not making a new point object here. We're not making a new vector object here. Right, so when we make the object, its position, that should be POS, that should be VEL, sorry, is the object at address 250. Right? And its velocity is the vector object at address 350. Right? So the projectile object has a reference to that object and that object. And the caller whoever made the projectile object, also has a reference to those two objects. Right? So there's the code there, right? So what happens when you change the position and velocity of the ball? Wait, set velocity to, there's a lot of mistakes on this slide, VEL. Okay, so what happens when you set the position and velocity of the ball? Right? So if I ask the ball for its position, right, and then I write, is the ball position the same object as that object there? Right? That's what equals equals does, right? For two references, is that the same object as that? That prints true. Right? So in other words, the projectile, right, its position is the same object as that object there. Right? In other words, nobody owns the position exclusively. Right? So in other words, the ball position, right, which you can see right here, right, is the same object as or refers to the same object as the variable POS. Right? They're both the same value, so they both point to the same object. Right? They both point to that object there. What happens if you change? So if the writer of the main method, if they change their variable POS, right? So if they take their variable POS and they change it to -99 and -22, right? And now you ask the ball, hey, what is your position? Actually, I don't even have to ask the ball for the position. I've asked for it here. If I just print out the ball position here, it prints out -99 and -22, right? So without even asking the ball for its position again, right, it seems to change. Right? You actually will get -99, -22. Why does it change? Right? Because that object, right, POS refers to that object there, right? And whatever's returned by ball get position also refers to that object there. Right? If you change that object, right, then the ball also sees the changed position. Right? What does that mean? You can change the position of the ball without telling the ball to change its position. Right? You can just mutate the variable POS. Right? So what happens when you change? So when you write POS.set -99 -22, right? The coordinates of that point change. Right? What's the position of this ball? Well, it's that object right there. So the ball's position also changes. Right? So if somebody can get a reference to the position or velocity of the projectile, right, then that person can change those quantities without going through the projectile object. Right? So in other words, you don't have to tell the projectile to move, it will just move. Right? And that's not a flaw. Right? So that's not saying, so what I'm not saying is that you shouldn't do this. Right? So it's not a flaw of aggregation. Right? This is a perfectly valid way to implement the projectile object. Right? It's just that you have to be aware of what can happen when you do it this way. Right? So it's not a flaw, it's just a consequence of choosing to use aggregation. Right? Your object, my point object, my projectile object, might change its position or velocity even if I don't ask it to. Right? So you, as the user of this class, you just have to be aware that this can happen. Right? And it's not a flaw. Right? Now if you think it's a flaw, right? So if you think, hey, the projectile shouldn't change its position if I don't ask it to, right? Now you have to do something else. Right? So now you have to use composition, and we'll talk about that next day, because I don't want to get into that with only 4 minutes left in this class. All right, does anybody have any questions? All right, great. I will see you next week.